Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about the rectified voltage. So let's get started. Alright, so when we're talking about a DC voltage supply, there are several concepts we have to get across, alright? So let's just talk about the first concept. This is my attempt at drawing a sine wave, okay? So this sine wave we have to change. So instead of being that variable, the final output is a DC voltage. This is what you call AC, alternating current, right? Assuming this is your zero line, above here it would be a positive voltage, which means it's going in one direction, and below the line it would be a negative voltage, which means it's going, the current's flowing in the opposite direction. All right, and this you can think of as DC. This is what you would see on an oscilloscope. So depending how you set your oscilloscope up, this might be, say, +5. It would be 5 volts. It could be 9 volts, 10 volts. But the point is that you notice it's not wavering, it's constant. That's what you're looking for, okay? So how do we get this? And this is what this video is about, okay? So the next thing we got to talk about is the transformer. So when you're going through, there's your AC signal. Now suppose you went to a wall socket. Your wall socket has this kind of AC output, okay? It's 120 volts RMS. And the frequency is at 60 hertz. That's how the United States does it. Different countries, you're going to have different values, okay? I think Europe has 50 hertz instead of 60 hertz. Okay, but you see what's going on. So let's take this and let's go into what we call a transformer. A transformer basically takes this voltage, puts it into a magnetic field. Via that magnetic field, it transfers it into another coil like this. So if your 120 volts was coming in here, this would be your primary side. Now how I'm drawing it, it's from left to right, okay? I've never seen it right to left, but you could see it like that, all right? And this is your secondary. All right? Now, N, small n, that equals the number of turns, right? So each side here has a different number of turns. And generally, how they show this is you may have, suppose you have 10 turns over here. It goes around 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this one may have 5 turns, say. So it's going to come 1, 2, 3, 4, 5. So the turn down ratio, or the turns ratio, is defined as, and this is via IEEE, okay, is going to be the number of turns in your secondary divided by the number of turns in your primary. All right? And that's going to be equal to n, small n, that's what they call it. So actually I drew small n here. Actually, in the text that we have, or that I've seen, sometimes the number of turns in each side can also be written as a capital N, but the turns ratio that I've seen is a small n. All right? That's supposed to be an n there. Please forgive my poor penmanship here, okay? So in the example above, since this is your secondary side right here, and this is your primary side over here, the turns ratio, n, let's just draw n, would equal 5 over 10, wouldn't it? Which would be equal to what? 1/2. Now, let me tell you something. The voltage in the secondary is going to equal N times V primary. In this case, N is equal to 1/2, right? So let's fill it in there. Your primary voltage in this case was equal to 120, wasn't it? So in this case, it's going to be equal to 60 volts RMS, and this is V secondary. Got it? So, depending on the number of turns, depends on what your secondary voltage is going to be in relationship to your primary. In this case, the secondary voltage went down, didn't it? It went from 120 in primary to 60 for secondary, right? So this is what you call a step down transformer. Got it? Now, you can just as easily have had this, instead of 5, you could have had this be 20. In which case, if you did your numbers again, you would end up with V secondary is equal to 240 RMS. All right? Let me just rewrite that neatly for you. I'm sorry. I get too excited when I'm writing, and anyway, you can see my writing gets bad. 240. In this case right here, your voltage went from 120 to 240. This would be called a step up transformer. All right? All right. Now, since we have an understanding of what a transformer is and what it does, now in the next section we are going to discuss 3 methods of creating a rectified voltage. See you soon. All right, everybody. So what I did is I redrew a circuit here. This item right here is what we call an AC source. All right? This puts out a sine wave. All right? Now, with the sine wave, like that's supposed to be a straight line. This is what we said is positive, and this is negative, all right? So in this region right here, we have a positive voltage, get it? So you're going to have a positive voltage going this way, right? Now it's going to go through your diode, and then it's going to come down and go through your load resistor, all right? Now, remember, what's your voltage drop across a diode? Assume it's a silicon diode. It's 0.7 volts, right? When you look at this signal coming in. This top part up here, the top, very top of that, that's called V peak. Okay, sometimes it's just denoted as VP. All right. So the peak voltage going across this load resistor, all right, is going to equal VP of your AC source minus 0.7 volts. Got it? Now, tell me something. When this AC source gets in this row, it's negative, right? Negative, it's trying to push current this way, isn't it? Based on what you know about a diode, is it going to allow current to flow in that direction? Well, the answer is no, assuming you didn't exceed the breakdown voltage. Alright, so no current's going to flow in that direction, so there's going to be no voltage across the load resistor. The resultant waveform of what I drew right here, it's going to look like this, right? It's going to start, if we're looking at this right here, it's going to start, go up, and come down, alright? We got that, and the peak is 0.7 volts below what you're starting with. We get that. Now, if your signal goes negative, like it will, the voltage across your load resistor is going to stay at 0. Why? Because the diode won't let current flow in that direction, so it's just 0 volts. Then your AC signal is going to come back. Again, it's going to go up, come down. Guess what? This is going to repeat. This is this here is what your source is doing. This is what your voltage looks like across your load resistor. So basically, if you take these away, this is the waveform you'll see across your load resistor. Alright? This is known as a half wave rectified voltage. Okay? Now, there are some useful equations that go along with this. One of them is your average voltage is going to equal VP, which is your peak voltage, divided by pi. Alright? The other important thing to think about is your peak inverse voltage. Okay? That's going to equal VP in. The peak inverse voltage is the amount of voltage seen going this way. Now think about it. Why is that important? The important thing is you don't want that voltage to exceed the breakdown voltage, right? If it exceeds the breakdown voltage, then you're going to have current flowing in the opposite direction. So you have to make sure that your diode can withstand the peak inverse voltage that's going to be placed upon it in your circuit. Okay? Now, let's try something here. If we take a transformer, let's suppose we have an input here like we just had. That's your source. This is your primary. Now, you're going to the secondary, aren't you? Right? Take this, we go through a diode. The diode then comes down, goes to a load resistor, RL. And simply, it's like this. That's basically the same circuit we just drew, right? If you take a voltmeter, we touch each end here. This right here is your V secondary. It's across each side of this transformer. Same likewise, this here, that's your V primary, alright? Again, the thing to remember about this is, remember, you're going to have a turns ratio here. Suppose it's 2 to 1. That means your V secondary is going to equal 1/2, because this is equal to N, isn't it? 1/2 your V primary. Alright? So when you know what that is, and depending if you have RMS or peak, suppose it's peak, you can simply check, you know, the peak voltage is going to be going across RL. That's simply going to be V secondary, or VP secondary for peak, minus 0.7 volts, right? And then you know the voltage that is going to be dropped across this load resistor. Alright, I will come back shortly and we'll talk about another circuit for rectification. See you soon. Alright, so let's look at another waveform, shall we? We started last time working with something that looked like this, right? This is half wave, right? Half wave rectified voltage, right? Half wave. What about this? You notice there are no flat portions here, right? This is known as full wave rectified voltage. You got that? The key thing is, for half wave you can recognize it by these zeros, right? Full wave you can recognize it because it never goes to zero. It's just the same thing over and over and over, right? So think about it. How could you design a circuit to do that? Well, there's two ways we're going to discuss this, right? One of those ways is you have transformer coming in, right? You're going to have your source. Just connect to it here, and we're going to connect to it over here. This is your primary. We can do the same thing here on this side. And this is your secondary. Now, this transformer is slightly different than what we've shown you before, what I've shown you before. It's called a center tapped, which means in the center of the secondary, what this means at the center of the secondary, you have a connection to ground, all right? This is your center tap right here. That's why they call it center tapped. The resultant waveform voltage is you have a waveform here, right? And you're also going to have a waveform here. Notice they're out of phase. This goes up and comes down and back up. This goes down and comes up and back up. So they are out of phase, all right? So this voltage, the amount of it, is equal to V secondary divided by 2. Each of them are equal to V secondary divided by 2. All right. Now, let's just continue with this, shall we? Suppose this just continued over here. Now, what would happen if we put two diodes in here? Let's call this diode 1 and diode 2. We connect them together over here. Come through, come down, go through your resistor, and bingo. This is your load here, for example. All right? So there we have a circuit which will result in a full wave rectified voltage, right? Let's just go through it. So in one direction, when your primary is in the positive part, right? What's going to happen? This transistor's going to be on, isn't it? So you're going to have a positive voltage here, right? That's what it shows right here. It's a positive voltage, right? So you're going to have a positive voltage here. This voltage is going to go through your diode, through your load resistor to ground. Got it? So your output is basically going to look like this. Got it? Now, you know there's a diode drop here like the other one, so your peak here is going to be 0.7 volts less than your V secondary over 2. We'll talk more about that later. Now, the next part is this part. What happens now when it does this? Now, if you notice, this part here goes negative, doesn't it? But this part here goes positive. By the way, before we even go there, I forgot something. This is positive. When this is positive voltage, this is negative. That means this diode is biased in the wrong direction. no current's going to flow that way, right? So this one was on, and this one here was off. Get it? Now, when it flips the other way, this one is off because your voltage is negative. You have negative here, you're going to have positive here. It's trying to push the wrong way. It's going to be off. And this one will be on. Notice you have a positive voltage down here, right? Positive voltage. You're going to have a positive on this side, negative here. It's just going to go right through. You're going to have one voltage, a diode drop here, right? Across there, and it goes through your load resistor. So you're going to have the exact same signal, aren't you? Again, this is going to be one diode drop less than your VP secondary over 2, all right? So if you really want to think about it, this right here, this value at this point, that's going to equal, I put it right here, that is going to equal VP secondary over 2 minus 0.7 volts. There's your diode drop right here, and this is your secondary voltage for your center tap transformer. All right? And there, when you do that, look at your waveform. That is a full wave rectified voltage. All right? Let's do one more, and this other one we're going to do is going to be slightly different. The fact it's going to use a bridge, okay? By the way, when you're building these things, look at the direction of your diodes. If you notice, they're pointing away from your transformer, okay? So that's going to help you when you're building them. Okay, see you soon. Alright everybody, so what I've done here is I've started drawing a circuit for you. Obviously this right here is a transformer with the primary side on the left and the secondary side on the right. Alright, here's your AC voltage for your primary. Obviously you're going to have a turns ratio here, right? You're going to have a number here for your secondary, a number here for your primary. We've already discussed that. Really, what I wanted to talk about in this last portion here was your bridge rectifier. And you notice that this comes down and we have something right here that looks like a diamond, right? Usually bridges are drawn with a diamond shape, okay? So I'm going to put in these diodes right here for you, right? So here's one, right? Here's the other one. Here's one. And here's one. I'm trying to draw those like diodes as best I can. If you notice, all of the diodes, right, are pointing away from the transformer, right? They're all pointing roughly in that direction. Got it? Let me draw that one just a little better here for you. I'll fill them in here for you. There you go. Let's bring this one over here like this. Make it look like a real arrow. There you go. There you go. Now, so you understand, right? This your transformer comes to this bridge. This side is going to come out. We're going to go through a load resistor. Call this one R sub L, right? Now, generally this goes to ground, and this other side of your bridge goes to ground, right? So what I'm going to do, I'll use this blue. Really, these are connected. It's kind of like in a loop, right? They're both going to ground, so they're connected. So what I'm going to draw now, I'm going to draw a dotted line. All right, so you can see them being connected, all right? Now, here's the thing about a bridge rectifier. And this is where it gets confusing, okay? So you need to follow along here. Suppose right now at this instant in time, there's two outputs on your, obviously on your transformer. And this output is at a higher voltage than this one, right? So this one's going to have a positive by it, and this one, the bottom one's going to have a negative by it, like I've drawn, all right? So think about it like a DC source, just at this instant in time. Your voltage, we're talking about conventional current flow now. Your voltage is going to go this way. Come down here, right? And look, it has to make a decision. I didn't draw that very well, but you guys get the idea, I'm sure. You come over here, and then it's going to come down. Where's it going to go? It can't go this way, can it? Because this would be reverse bias, wouldn't it? So it would have to go this way, wouldn't it? So I'm going to draw an X through that one. It can't do that. It's going to go this way. And then when it gets to this junction right here, it cannot go that way, can it? Because that would be reverse bias, wouldn't it? So there's only one choice, is to come out down through your load resistor, right? So it's going to go through your load resistor. It's going to come back this way. Back up here. Now it's going to come back here, and it has to make a choice. Now think for a second. Your potential, your voltage at this point, right, whatever you started with, your voltage is going to drop by one diode drop, which is 0.7 volts here. So this voltage at this point right here is going to be your 0.7 volts less, isn't it, than it was up here, than it started with, right? Then it's going to have a voltage drop across your load resistor. So this voltage at this point is going to be less than the voltage was here, which is less than the voltage was here. It just has to be, right? Then you're going to come back this way, all the way up here. So this voltage here at this point is going to be, this voltage right here is going to be less than the voltage over here. So it cannot go that way, right? Because it's reverse bias. The only choice it has is to go this way, doesn't it? And then it's going to come down through this line all the way back home, right? So if you follow that, it has to go through a diode drop right here, a resistor drop right here, and another diode drop right here. So think about that. What you're interested in here is, where do I have it here? Do I have it right here? Here it is. your V, your peak voltage, your output, right, is going to be your peak voltage from your secondary, right, which is between these 2 points, right, minus 1.4 volts. And this 1.4 is because you have two diodes, two diode drops, right? And each diode drop equals 0.7 volts, right? So hence 2 times 0.7 volts equals 1.4 volts, right? And that's where this comes from, all right? Now, let's do something else here. I want to do it in the other direction to make sure you really have this, okay? So let me, equation's obviously going to remain the same, but I want to walk you through it to make sure you really get it, okay? Here we go. Get rid of that. We get rid of this. So think about it. 4 diodes. You have 2 choices for your voltage, right? For your AC source. So when we just did this, 2 of the diodes were on and 2 of them were off. So by deduction, when we change the potential on the voltage, change the polarity on there, the 2 that were off were going to be on, and the 2 that were on are then going to be off. And that's what I'm going to show you right here. Okay. So, the other one I did in red. Let's do this one in green, okay? Let's try this one. So, if we change it now, you know what? I should get rid of this one, shouldn't I? I'm sorry. Gotta forget that right there. Alright, so let's do the next one in green. Suppose this is negative and this is positive. Alright? So at this instant in time, we know that these 2 wires, they're going to have a potential as shown here, right? So let's think about it. What does this mean? Well, let's go from, we usually go from plus to minus, don't we? Let's just follow it. Come down here, come down here. Now, we can't go this way, can we? Because we have a positive voltage here, right? And we're traveling in current, so we have to go in the direction of the arrow, right? So this one is off. So we're going to go this way. Then down across your load resistor. Then we're going to come back here. Continue back through here. And now we're at this point, right? Now think about it just like last time. You're at the highest potential right here, right? So at this point, right here, you're at a very high potential. You're at the highest potential, very high, that's relative. You're at the highest potential you can be, right? Because it hasn't had any drop. Now, then it's gone through a diode drop when it went here, right? So the voltage potential at this point after this diode is going to be whatever this potential is minus 0.7 volts, right? Then you're going to go across your load resistors, so your potential at this point is going to be even lower. It's going to be 1 diode drop and a load resistor drop, right? Depending on what your resistance is and current, right? Now, this is going to go that voltage is what's at this point, right? So look, your voltage here is higher than it is here, so this is reverse bias. So obviously we cannot go that way, right? The only way we can go is this way, right? Now, you're at another junction. Where are you going to go? Well, remember, this voltage right here at this point, you just got to follow your voltages and think about it, right? We just finished saying that this voltage here is one diode drop, but then it went one diode drop lower than your potential here, right? And then it went even lower here, so this is a lower potential, and it dropped again right here. So this voltage is at a lower potential, so this is reverse bias. It's not going to go there again, right? So that diode is off. So it only has one choice. It's going to come back this way, right? And again, as you can see, two diodes are on. This is on here, on, and this is on over here. I'll say, well, I'll put the on over here. And these two here and here are off. And so you can say again that VP out equals your VP secondary minus 1.4 volts. Okay? That is how you work with how a bridge diode works. Now look, when you have these diodes, okay, they're going to look like this. And usually they have a stripe on one side or the other. When you look at them, schematic format, what that means, this stripe they have on the diode is this little bar right here. That's what it means. So it helps you orient them right. So conventional current flow goes this way. All right? Be careful when you're building the bridge rectifier, and make sure that your diodes are all pointing in one direction. All I can say is I've seen a lot of diodes smoked because that didn't happen. I saw one where they had a pair of diodes that were pointed this way and the bottom set was pointed the other way, and it didn't turn out very well. Let's just say there was some smoke in the lab, okay? All right, everybody. There is your bridge rectifier. I hope this helped you, and I will see you soon. Bye-bye.